Uh, how are you, Yashodhan, with the course? Are you able to follow the content?
Yes. I've been doing that. I went back to all the lectures and went through them again. Um, uh, Last 3, 4 weeks, 2 weeks, we got some breaks, so I went through them again. Um,
Good, good. Okay, we're actually completing a lot of wonderful things now. Um, we just have a small thing to do, and after that, connectedness. With that, we'll be done. But if you wish to think about little algebraic topology, we can do it. But I think we can conclude the topology to some extent after we finish connectedness and yeah, there is connectedness, simply connectedness, total connectedness, whatever it is. So today, what I want to do is okay, if I have a maybe topology, see you, I hope you will understand, appreciate that compactness is something very will allow you to have a lot of control on yourself. If a space is compact, it can be covered by finitely many, open sets. And if a subset of a topological space is compact, every cover, if it's a finite subcore, that means you can handle it only with finitely many open sets. That's quite easy. That's quite nice. So if the space is not compact, it is a little unwieldy. That's what I think the word itself tells you that literally, something is compact, something is not compact. Okay. So the choice of the words in topology are very, very nice. The choice of words we are using it actually suggests of the, literal meaning for a layman. So now, if I have taken just a regular, completely regular, arbitrary, completely regular place, suppose I have taken that. Um, we want, if this is not compact, we want to, uh, sort of embed it inside a compact space. That's what our aim is. Okay. That there are many ways we can embed that space in another compact space. One of them is stone set compactification, which is what I will talk about it today. Later on, we can talk about some other compactification too. Why not? Okay. So, okay. So I have a completely regular space, but it is not compact. So what my object is to embed it into a bigger space, which is like some beta X, which is actually compact Hausdorff space, and so that you have a one-one mapping going into it, right? This is what I would like to really do. Okay, uh, and we do it in a very nice way. I'll tell you step by step. So let us see. The theorem we are doing is what is called Stone's compactification. I should have done an easier compactification first, but doesn't matter. Doesn't matter. We can just do this. It's in this in the flow of the things we've been doing for quite some time now. Okay, let X be a completely regular topological space. Let X be a completely regular uh, topological space. Okay. Uh, then there exists a compact Hausdorff space beta X. Then there exists a compact Hausdorff space uh, beta X. Okay. Uh, so that this X is embedded into that. So X can be actually X is embedded means X will have a copy inside that. Okay. Some copy. That embedding is F maybe. Okay. Embedding means this is a one-one mapping. And this X goes to Fx. Fx is a subset of beta X. Okay. And this Fx is dense inside beta X. That's how you choose it. Okay. Then there exists a compact Hausdorff space beta X with the following properties. One, X is a dense subspace of beta X. One X is a dense subspace of beta X. As I can identify this with fx. F is a 1-1 continuous and onto mapping. You identify this x and fx completely, and that you say that x is a subset of subset of subspace of beta x. Is that okay? That's what you're saying. X is a dense subspace of beta x. Okay, dense subspace of beta x. And two, uh, every bounded continuous real function defined on x. Every uh, bounded continuous real valued function defined on x. Okay, x is sitting inside beta x. So so this is x and this beta x, and I have a continuous function from x to r, then the theorem says that I can extend it to a continuous function on beta x. So every bounded continuous real valued function defined on x has a unique extension, as a unique extension to a bounded continuous function, real value function, bounded continuous real value function on beta x. Okay, so it's like I want to study the space x, but I embed this space x into a compact space, and I'm studying continuous functions and f on a lot of continuous functions and x. But if I want to study x, I want to study it as a subspace of beta x, right, which is a compact Hausdorff space. So continuous functions are x. If they can be extended continuously to beta x, then the study of the functions f on x will be relegated to will be switched on to studying the continuous function on beta x, and maybe make the inferences of those things back into an x. That's a simple thing I want to do. Okay. This is a little bit of a tricky proof. Uh, at the end,
And
after you go through the whole process, it is not a difficult proof. Okay, please, you were saying something.
so, and this is a unique extension. There's only one extension that is possible on that.
Yeah,
That is very interesting.
yeah.
Okay.
That is actually very easy at that. That only one x. See, you have here x is dense in beta x, and I have a function, maybe f from x to r. I want to extend it to capital F uh, from beta x to r. The fear is if I have two things, f1, f2, will they be same? That will be a very easy exercise. I will show you towards the end there. Uniqueness is, in general, forget about all these spaces and so on. If we have a dense subset of a topological space X, and if you have a continuous function f from A to R, if it can be extended to a function g, maybe g or g dash, the two functions from x to r, which are continuous to and g restricted to a,
Eh,
is g dash restricted to a is f. All this would imply g equal to g dash. It's a very general thing. I can easily prove this. Maybe we'll just think about it once before we go further. Okay, we just want to feel comfortable about the statement of the theorem and how a proof is given and so on. After going through the whole process, then we realize that we can prove it easily, but there are a lot of steps involved. Okay, let's say it's a digression. Rather, last step, the uniqueness I'm talking about it. You asked me, right? Very easy, sir. Um, Actually, R is a Hausdorff space. It separates points, right? Suppose I have two functions g and g dash. So the g and g dash are different. Then there is an x in x such that gx is not equal to g dash x. Isn't that right?
right?
But g is a continuous function. So First of all, Gx is not equal to G dash x. These are two elements in R. Because R is a Hausdorff space, I can find the two different open sets. G1 and G2 are open sets in the topology of R, such that G1 and G2 intersection is empty, and Gx is in G1, and G dash x is in G2. Is that right? Okay, I can do that. But look, G is a continuous function, so F inverse G1 is an open set here. So that F inverse G1 is your H1. H1 is F inverse, not F inverse, G inverse G1, and let's call it H1 or what? Yeah, and H2 is G dash inverse G2. These are open sets because G and G dash are continuous functions, right? And both of them will contain X. X is in H1 intersection H2. If I call that one H, so what I say that I have H is a open set in X, okay, and X is in H, and you see that G of H is contained in G1, and G dash of H is contained in G2. These are disjoint subsets. This is subset of G1, that's a subset of G2. But X is in H. H is an open set containing X. To start with, where do you start? X is in A bar. X is A bar, right? So small x is A bar. That means A is dense in X. If X is in A bar, every neighborhood of X intersects A. And this H is a neighborhood of X, and that intersects A. So A intersection H is non-empty. So suppose I have chosen Y in A intersection H. Okay, now I'm in trouble because I already told you, because GY equal to G dash Y, because both of them are in A. But GY is in GH. G dash Y is in G dash H. I'm very sorry to say that these two are disjoint subsets, right? This is contained in G1, that is contained in G2. GH is contained in G1, GH is contained in G2. I already said this somewhere, I think. So, yeah. There you go, I said that. G dash H is contained in G2. So there is a contradiction. Okay, so extension has to be unique. It cannot be too different. That's a kind of a problem I should have given as an exercise in the beginning after defining what dense set is. Okay, right. We'll unnecessarily we'll write the proof one more time at the end. Not a problem. This is something I should write at the end. Are we okay, or any question on this?
No, that's good. Thanks.
Okay. Okay. I want to prove this. Before proving this result, let's just make a couple of comments. Before proving the result, I have explained some of these things before to result. Let us look at the note. Note. I give you two notes. One of them. I already said that if X is a completely regular space, okay, completely regular T3.5, I can start using this language also. If you look at the space of all real valued bounded continuous functions, which is CXR, it actually separates points in X in the sense that if you take two different points X and Y in X, I can have a function which takes different value at X and different value from Y. Okay, for each X and Y in X not equal to Y, there exists a function F in CXR such that Fx is not equal to Fy. That's one property. I use this property very nice. This property is easy because see, T3 and a half means T1 also. So singleton X is closed, singleton Y is closed, and X is an element, and X is not in the closed set A. So you can have a function F, a continuous function, bounded continuous function. Actually, continuous function from X to remember 0, 1. That's what completely regularity means. So that f of x equal to 0 and f of a equal to 1. In particular, f of y is 1. Therefore, fx is not equal to f(y). So, right? So, space for continuous functions separates points in x. But something more I did is that this is the family of functions from x to r. And the smallest, the weakest topology in x with respect to which all these functions are continuous is actually the topology I already have an x. See, if they are already continuous, the inverse images of open sets, their functions from x to r. Inverse of open sets are already open sets in x. X already has a topology, completely regular topological space. It has a topology. So if every function is continuous, all these inverse images will be in that. But the weakest topology with respect to which all these functions are continuous is the weakest topology I can create with only inverse images of open sets under the functions in that. They're already there in the topology of X. That is why they are continuous. That means the topology of X that is already existing is stronger or finer than the weakest topology with respect to which all these functions are continuous, usually. But in a completely regular space, both topologies are same. I already have a topology on it, but I can also create the weak topology coming from these functions. That weak topology matches with the topology. I proved it to you already once. Maybe I will prove it one more time. Okay. So what is this comment I want to make? If X is completely regular, the the weak topology uh, generated by family of continuous functions, bounded continuous functions, real valued continuous functions is same as the topology annex. I will prove this to you. Okay. One more. This is also not a very impossible thing. Actually, these are all the things we should be comfortable with. If you really look at a product of, I will prove this one and this one a little bit before I start the proof of that. If I look at the product space of a lot of topological spaces, this is the indexing set delta. If I take a product space of a lot of topological spaces, if I call this X, to X alpha, maybe to X beta, I have the projection map phi beta, right? What is an element in X look like? An element in X is like a family of these things, right? This is how an element in X will look like. So what does the projection map does? It just sends it to the beta coordinate. This is the projection map. Okay. Actually, the topology that I have given you on the product space, so-called product topology, is the topology generated by inverse images of open sets under these projection maps. So phi beta inverse G beta, where G beta is open in X beta, all these things will form a subbase for a topology and the product space. That is the product topology. We have two topologies, product topology and box topology. We're not talking about box topology. Product topology is generated by these subbasic open sets. What do you mean by subbasic open sets? That means their finite intersections are open sets. What are finite intersections of them? For example, finite intersections of them, okay, is really what is this phi beta inverse g beta? It is like in this entire thing, in the beta component I put g beta, everywhere else I put X alpha, X alpha, X alpha. X alpha means X alpha dash, alpha double dash, X1, whatever it is. All the things are full copies. Only the beta component is G beta. Right? What is that? How can an element belong to that? Something belongs to this only when phi beta component of X is in G beta. Is that right? So beta component must be G beta. Whereas the other components, they can be anywhere. So inverse image of an open set G beta and X beta by pi beta is really all full copies in the beta component 1 G beta. Their finite intersections will be in finite of the copies beta 1, beta 2, and so on, beta k. I have these open sets. Everywhere else we have full spaces. X alpha dash, whatever is the indexing set. The rest of them are all X alphas. And only in finitely many places I put G betas. That is how basic open sets in the product topology would look like. Sounds good? This is all revision, right? Now if I take a subspace of that, subspace of the product space. Oh, okay, maybe before that, I should have said this also. So all these projection maps, actually, they give you the basic open sets here when you, sub-basic open sets here when you pull them back. Open sets are pulled back, you get sub-basic open sets. It turns out that all these projections are continuous on account of that, because I'm calling all the sub-basic open sets, right? So the projection maps are all continuous. Indeed, I proved it that time. The topology, the product topology, is the weakest topology with respect to which all these projection maps are continuous. Okay. And now what I would like you to think about is if Y is a subspace of that, then the restriction of pi betas to Y alone will also give you some projections. And the topology that Y inherits from X is same as the topology, which is the weakest topology with respect to which all these restrictions of pi betas to Y are continuous. Let me state that. Okay, uh, you know, it's not impossible, but um, the sentences are too long. What is the next note? Next note, if Y is a subspace of capital X of the product space. When you say product space, space with product topology, okay, not any other topology. Product space X equal to pi X alpha alpha in some delta, okay. If Y is a subspace of that, the topology Y inherits as a subspace of X. Y inherits as a subspace of X is same as the weak topology on Y generated by the family of all by the family of all projection maps, projections restricted to Y. Family of all projections pi beta x2 x beta, Y is only a subspace of X. So pi beta is defined on the full space X, and that has to be now restricted to Y. So projection maps pi beta x2 x beta restricted to Y. Okay, these are the two things. I have done this and I didn't do it, but it's I did it in the case of the full space. Uh, Same kind. Well, let me spend some time on these things first before I start my proof. Okay, are we good with that? Questions?
No, I think this is good.
I will explain this maybe once. I can give a simple proof for that. Right. So what is that? If the space is completely regular, the weak topology generated by CXR is same as the topology NX. Let me just explain that. Okay, this is not the proof of what we are really looking for. Yeah? So note one, proof of one. Proof of note one. Look, since all members of CXR are continuous functions on X. That's what the definition of that is. Boundary can be are continuous functions on X. Okay. Because of that, all the inverse images, F inverse G, G open in R, F a function in CXR, they're all open sets. In X are all open sets. In X, which already has some topology. In X, oh, that means, yeah, these are the basic open sets which will generate the weak topology. Weak topology is the weakest topology, which makes all these sets open. They're all open on account of the topology I already have in X. So the weak topology generated by all these functions is weaker than the usual topology. Therefore, topology on X is finer than the weak topology on X generated by CXR. And same ideas we'll use again later on. Okay? Did you get that point? What I have to show is that the topology on X is finer than the weak topology on this, right? Now I have to show that the topology on CXR is finer than the topology on X. Then we are fine. Okay? I want to show that the topology generated by CXR is finer than the topology on X. Okay? That means if you take any open set in the topology of X, if you want to say that this is the final and those basic open, and you take any element X in this, you should be able to squeeze in between such a basic open set of the weak topology generated. So this X should belong to some F inverse, some H being an open set in R is contained in G. If you can manage this, then you are saying that, look, the really open set that you have in X, how are they prepared? They're prepared by these kind of things, and these will serve, these will generate the entire topology in X, because every X and every open set in between, I am able to squeeze something like that. Is that clear? So take any open set G in X and let X belongs to G. You know what? Then X is here and the G complement is a closed set. This is a closed set. And this point and this is a closed set. And because the space is completely regular, I can separate them by a function. Okay. Then G complement G complement is closed and X is not in G complement. Therefore, by completely regularity a property of the space X, there exists a function f, continuous function from X to 0, 1, uh, such that okay, f of x is 0 and f of g complement is singleton 1. Therefore, because of that, x belongs to f inverse 0 to 1 half, okay, which is contained in G. Because G complement is going there, so f of G complement is therefore contained in f inverse half to 1. Half to 1 is an open set in right hand side 0 1 is open in 0 1. So open set is inverted, you get an open set. So G complement is contained in this open set, but that open set is disjoint from this open set. So G complement is contained inside means its complement, which is this, this and a little more also is contained in G. Yeah, that's good. So what did I do between an open set in the usual the topology X and an element in that? I'm able to squeeze in the basic open sets that will make up your weak topology. So therefore, weak topology generated by CXR is finer. Yeah. These are granulated even further. Is finer than topology NX. Okay. Good. I will just leave the note 2 for you. Okay. Leave note 2 to think about. Note 2, I have done the note 2 in the case Y is the entire space, and similar such argument will go with that. Okay. This also is presented this one. So let's go back. Is that clear, sir? Any question you need to ask?
No.
We not started with the theorem yet. Okay. Let's go. Let's come back to the theorem. Huh? My whole idea is to embed this completely regular
Marvelous
topology
contains a
space.
built-in screen reader called VoiceOver. If you know how to use VoiceOver, press.
I'm sorry. Oh, there was just something talking, maybe instrument talking. I don't know.
Yeah, sorry. The other laptop is talking.
That's fine. I understood sufficiently. Okay. So we started with a completely regular space and we want to embed it into a bigger space, which is a compact Hausdorff space, certain properties. First, let us look at this embedding. Okay. I want to put X inside a big space. Okay, let's go. The proof of Stone's compactification. Okay, so what I'm going to do is, okay, CA, what I want to do is, I have the CXR, right? This is a big family of functions, continuous functions from X to R. I want to list them all. I can actually take this as a list itself, but let's say I have listed them all as some F alpha, alpha in delta. Some indexing is done. How does anybody do the indexing? Well, each function can be indexed by itself. Taken as an index. So each F is an F. I hope you don't mind that, no? Right? Let CXR, all the functions, I want to have names to them, right? Some names, so I call them F alpha, alpha belong to delta. Okay, sounds good. And each f alpha has some range. It's a bounded continuous function. So because it's a bounded continuous function, it is bounded. So the range is a bounded set. I can make the smallest possible, range is a bounded set. So smallest possible bounded set or the compact set which contains the range can be found. So let I alpha be in some sense, maybe the infimum of all f alpha, and supremum of all f alpha. So this is like uh, greatest lower bound, GLB, of G alpha and the least upper bound of G alpha. So that will be the range. You don't go anything beyond that, right? That is I alpha for each alpha in delta. So I have
So the
created a.
range,
Huh?
but the ranges of alpha, when we say infimum, the ranges of alpha may not contain each other, right? So if there are
F
two
alpha, yeah,
disjoints,
I
yeah,
alpha is one position. I alpha is a actually this GLB net may not be achieved by G alpha anyway. The range may be open interval only, but I have taken the smallest closed set which contains the range of F alpha. So F alpha's range is calculated, and I have taken the smallest closed set, closed interval that contains this. That closed interval is I alpha, is the smallest closed interval containing that. For each alpha, F alpha has a range. That range I want to write it compactly.
hmm.
Is it clear?
Right, right, yeah,
I have maybe one function is sin x, so I say it is -1 to 1. And one
right,
function is maybe sin squared x. I say the range is 0 to 1. Actually,
yeah,
here endpoints are also taken, endpoints
yeah,
may not be taken.
yeah,
Let's say for example, right, you understand that 1 by
yeah,
x squared plus 1, the range is 0 to 1. But I will take this interval 0 to 1. Okay. Greatest
yeah.
lower bound will be 0. 0 is not, okay, and nothing else is a greatest. So that's what I'm doing. For each f alpha, there is a range. I don't want the range. I want to take the as small as. Of course, range is that, but the closure of the range is what it is. I could have just called I alpha to be the closure
Closer of,
of range of f alpha, closure in the R. We know it's a compact set,
yeah.
so it has to be some set like that and connected to. We didn't talk about connected, but something like that. Is it clear to you now?
Yep, yes, yes.
And what I want to look at is I want to take X to be product of all these ranges. Okay. Each I alpha is compact and Hausdorff, and therefore by Tikhonov theorem X is compact too, and then it is Hausdorff. So then X is a compact Hausdorff space. Oh, excuse me. I already have the X. I should have a different name to this. Let's say P. Then P is a compact Hausdorff space. Okay. I am going to embed X inside this P. So I want to define this into P, a function. Define, maybe I should use some other name, H or something anyway. Define f x to P by f of x equal to f of x should be an element in this product. So f of x should be, right, many entries there. For each alpha there is an entry, right? And what do I take? I take f alpha, the function is there at x is what I take. Okay. So what am I doing? You understand that? So in a sense, X is taken to be a subspace of product of, okay, closures of ranges of F, where F itself is a continuous function from X to R. That's what I'm doing. In the right hand side, for every function, I look at the closure, I look at the infinite product, and I want to, however X is being embedded into that. Okay. So every continuous functions, evaluation of X is written here. Frankly speaking, I can write it as Fx. Then I should use a different name in that case. If I use a name H, I'll just use the same name only. I think it's convenient to me. I should define it like this: Hx equal to Fx Fn Cxr. That's what this is. Instead of writing that way, I wrote it another way. Okay. See if you understand this. Okay. I think it's nothing much, but a little confusing at first, but it is not. Define F from X to P by F of X is equal to F alpha X as alpha goes to delta. That is what I said. Instead of F, I use the symbol H. X2. What is P really? P is closure of range of a function. Each function is function from X to R and its closure, and all such products are taken when F is in CXR. Instead of writing this way, I started writing that way. That's actually better. A lot of people do it this way also. This is more confusing. If that is confusing, then I look at it. Okay? You understand this? Each element goes to what? Evaluations of all different F's of CXR at X. All the evaluations are done. Okay. Now, please.
So even though we defined P as the product of all closures of ranges, but the definition of F is on not using elements in the outside of the range, because
Yes.
definition of F is still taking values on in the range itself. But we created that because you wanted to make a T2 space, I guess.
Yeah, I just wanted to make sure it's compact, so that's why I'm taking closure. There may be a few elements which are not in this. Anyway, I'm only taking the elements which are in this.
In the range only.
Okay?
Yeah.
Now, what is this is a infinite product. So if you compose with pi alpha, circle F, maybe I say pi beta. Okay? Pi beta, circle F is what? If you take this function and take the composition, that means you want the beta component, that is F beta. Is that right?
Yeah.
Notice pi beta circle F equal to F beta is continuous from X to R for every beta in delta. Oh, that is what continuity of the function F is. Therefore, F is continuous. Okay? In the product space, we did that. If I have taken the product space, X alpha in delta is X. Any function from here to any place is continuous. If and only if you, if any function from, any function from a topological space to X is continuous if and only if its projection upon X beta given by pi beta, this composition is continuous. So G here, Y to X is continuous. G is continuous if and only if pi beta circle G is continuous. So that's why this is kind of. So since f phi beta f is are all continuous functions, therefore f is continuous, right? Agree with that? I will show you that f is 1 1 also. So on 2 it is, okay? I'll show f is 1 1 also. Since x is completely regular, you want to show that f is 1 1, right? If you want to show this f is 1 1, if you take two different elements in this, x not equal to y, you want to show that fx is not equal to fy, right? So take two different elements in x. Let x comma y belong to x and x not equal to y. Since x is completely regular, I explained to you earlier that it separates points. Okay, because x is a element and singleton y is a closed set. Completely regular means T1 is also there. Therefore, singleton is closed. This is an element and this is not in the closed set. So they can be separated by a function. That function is in the class CXR, which is f alpha, alpha and delta. Okay, since x is completely regular, there is a beta in delta such that f beta x is not equal to f beta y. Okay, sir? Therefore, fx is not equal to fy. Because fx is a big, family of elements, and right, fy is also a big family of elements. The beta coordinate of this family of elements are not equal because of that. Okay, and therefore fx is not equal to fy. Therefore, f is 1. So f is 1 1 and continuous. Thus, f is 1 1. Thus, f is 1 1 and continuous. So we can identify, we will identify x with fx. So fx, which is part of the P. So I can imagine that x is a subspace of P. Okay? Actually, it's not x, it's fx. It's a subspace of P. Is that clear to you? And with fx, in fx, we identify x with fx. What do you mean by that? I mean, yeah. Okay. So x is treated as a subspace of P. Now this is a subset of P, right? X is a subset of P. If X is a subset of P, X has its own closure, X closure, which I call X roof, is a subset of P. This X roof is what I call beta X. Let beta X be the closure of X and P. Okay. Then beta X is a compact subspace because this is compact. Closed subspace of compact space is compact. This is house graph. Okay. Then beta X is a compact subspace. I hope you are understanding the story, right? Okay. Beta X is a compact subspace. And you see X is sitting inside beta X and X is dense in beta X. Compact subspace index and X is dense in beta X. After all, beta X is taken as closure of X in P. Okay, I think we are doing well. Now, the little problem is, I said all these things. X is a subspace of B, P, right? Oh, therefore, X as a set in P inherits a topology. X is a subset of P, and therefore it inherits a topology. But mind you, X already has a topology. Oh, then I should be very careful. I should be. What if this beta X is a compact Hausdorff space with respect to the topology that it has inherited from P? Are you following me? But X is a subspace of that. But what is subspace of that? Oh, wait a minute. X already has a completely replicated topology on it. So I think I have a little trouble with two topologies are floating around. A topology that inherits from P and a topology which is intrinsically there. I will show it to you that both the topologies are same. Then X is genuinely a subspace of genuinely a subspace embedded in beta X with along with the topology, not as a set. Understand that, sir?
Yes.
Oh, I did quite a bit. Huh? So I may be a little fast in writing these things. Okay. Beta X is the closure of X in Y in P. In P. So I think I already should say here, right? Already there is a confusion. There are two topologies in X. Which topology am I talking about? I think I should talk about it before I say this. Anyway, doesn't matter. There are okay. So Madhuri, let me see if I can fix my language right. Yeah, I understood that. So even before I say closure, let me be a little more specific about it. X is a subset of P. So it has a topology inheriting from P. And the closure of the topology is beta X. Okay? Right? X, I will write these steps here. I will write whatever I wrote. I said things very nicely, but that was a little, vague. I heard that. X is a, uh, X is thus, X is a subset of P. Okay? Hence, X inherits topology, X inherits topology of P, and it becomes and is a subspace of X, and is a subspace of P. Okay, let beta X be the closure of the subspace X of P in P. I think now it's clear. Okay, then beta X is a compact Hausdorff space. Yeah, that's better. Okay, and X with that subspace topology is dense. X with that subspace topology is dense in beta X. Okay. Okay. Only thing is suddenly X inherited a topology, but X already have a topology. What are you going to do about this? X already has a topology that makes it completely regular. Okay. What about that topology? I have two topologies floating around. Okay. And my object is to show that look, the topology X already has is going to be the same topology. I got that. Okay. Now, how do I do that? When I look at subspace topology, I realize that the P is actually the product space. Okay. And if you really look at the projection upon any coordinate, that is the F beta. And therefore, this all those functions are continuous, I know. Okay, they're continuous because of the original topology. That means the original topology is stronger or finer than the topology I have just created. Okay, are you following me? And the other way around too, because we said that the topology inherited, I said the topology as it is finer than this. And the other way around, I told you in the beginning is if you look at a subspace, how do the subspace topology come from? Only because it's the weak topology generated by all these functions. Okay. So combining these two things, you say both the topologies are the same. I want you to read the, Simmons, proof. Essentially the same. Okay, you understand that? X already has a topology that makes it completely regular. We shall show presently. We shall see presently that that topology is same as the subspace topology. Actually, it's all done because what is the subspace topology? That is the topology that's weak topology generated by all the projection maps restricted to the subspace. But completely regularity says such a weak topology is the original topology. I think I've finished that. I don't have to again write too many things. In the beginning itself, for a completely regular space, how do you get the topology? Yeah, there is a topology, but the topology is the same topology as the weak topology generated by all the continuous functions on that. And for subspaces and a product space, the topology, subspace topology is also generated by the same way. So completely regular topology space that you have already, the topology is same as the subspace topology. End of story. I think I showed that. Now I have clarity there too. Okay. It requires you to sit there and do the, step by step and feel comfortable with what I'm saying. Okay. You need to, I understand, but I don't know whether you get it completely or not. Okay. Yeah. So by the two comments I made in the beginning, just before the proof, I see that, okay, by the actually in the Simmons, he did it even more generally. Yeah, I have just to look at completely this space. Anyway, by the comments we made just before the proof, just prior to the proof, completely regular by proof that X is completely regular. That X is completely regular implies that both the topologies are the same. Okay, so finally I have decided that yes, this embedding is a genuine embedding of the original topological space into P. Okay, so thus the embedding means having a continuous one function into that. Thus the embedding of x into beta x is that of the original topological space capital X into beta x, a compact Hausdorff stress. So that the closure of x is beta x. There is also part of the thing I accepted in the statement of the proof. Okay, we've done that. Okay. Now the statement of the, if you go back to the statement of the theorem, if you go back to the statement of the theorem, it says that every boundary continuous real valued function defined on x can be extended continuously to a boundary real valued function onto beta x. I want to show you that extension. Very easy to show you that extension also. Okay, so take any how the continuous functions from x to r look like. They all look like some f betas. Take such a f beta. You know what? Take any beta in delta. What is this f beta? F beta is actually pi beta circle f. Okay, remember that? And yeah, this is uh, uh, this is a function from what is f is a function from x to p, right? Okay. I want to extend it to beta x, right? That's what I have to do that carefully. Okay, take any beta in this. I want to extend this f beta, right? Beta x is already a subset of p, right? So there is an embedding already. Beta x is inside p. That's actually sitting inside that. That's right. Beta x is sitting inside that. So, right? Let f be the beta x is sitting inside p. This is the identity function. Okay, and for every beta in delta, f beta is nothing but pi beta set left. That's it. Yeah, pi beta set left. What if I that is sitting in there? Okay, I have produced f from x to beta x, and beta x is in p. Okay, yeah. So what is the extension to the beta function? That's not the extension. No. The extension is going to be the following. I have to, yeah. Pi beta circle. F is the extension. Correct. Okay. F beta equal to pi beta circle. F. Yeah. Pi beta circle F. Okay, correct. pi beta circle F. Now, F beta restricted to X is actually F beta, correct? Is actually is pi beta circle F restricted to X. Good. Can you hear me well?
Yes, yes.
We're done. This is the extension. Okay. Therefore, that gives us the extension. Okay. So I said in my statement of the theorem that I have such an extension, and the uniqueness of the extension is easy exercise. And the uniqueness, because I explained it earlier, right? Uniqueness of such an extension is the following easy exercise. Is the follows from the following. Is an easy exercise. Is an easy exercise. What is that exercise? Let X be any topological space. Maybe I don't need X be any topological space. A be a non-empty subset of non-empty subset of X. Okay. Any function continuous from A to R and bounded can at best have, I don't even know if boundedness continuous is okay. Any F from A to R continuous can actually, I can do better than that. Let Y be a Hausdorff space. Instead of R, I'll keep out the Hausdorff space on the other side. Okay. Then if then any continuous function F from A to Y can have at most one continuous extension to A bar. That's what I proved in the beginning. Okay, right? Yeah, because of that, that uniqueness follows from the next. That's the theorem set. Okay, I will just basically maybe review that. Good. The space X is identified with a subset of the subset is fx really inside P. What is the P? P is the product of all ranges of H. Maybe I have to use some other name. Maybe phi of X bar phi belong to a continuous function from X to R. So I identified X with the images of all functions that I can have on X. Yeah, a function, an element in X is recognized by its action, by the action of all the functions on it. An element X in X is recognized by the action of all the functions on X. A different X, that is X is different phi, if you look at all the functions acting on Y, will be slightly different from all the functions acting on X. That's what the one-oneness came in. So an element is understood by knowing how all the functions are behaving at that point, and that is this identification. Okay, sir. You finished this result. I'm not going to too much on it, but I can probably just talk to you about another compactification. In a sense, this is a very nice compactification. This is going to give you a rich, very rich compact space into which X is embedded. I can have a very coarse compact space, very lighter compact space, not too many elements, but still it's compact. But like, for example, stereographic projection was not stereographic. If you really look at the plane, you attach an infinity to that and make it a sphere. Just by attaching one point, you make it compact. The whole plane is made into a sphere, right? That's a compactification. The sphere is compact, while the plane is not. By just attaching one point, I can make it compact. And that is actually what is called one point compactification. I'll talk about that also very quickly. And then I think I can take that much time on that. Let me see. Yeah, we can probably do that. Hmm? I'm not going to talk too much about it. Already we'll be talking many things, so uh, we will not say too much more about this compactification. Just want to understand where it is. Okay. Also, one point compactification. If you really look at the plane is compactified, right? The plane is compactified into a sphere. You put the north pole, that is the infinity. North pole is identified with all the points at the ends of this. Okay, and what is the neighborhood of infinity? Neighborhood of infinity will be this complement of the compact set. This is the neighborhood of infinity. Actually, if you project it, what do you get? On the plane, you get a big circle. Everything outside is the, in the plane,
Yeah.
everything outside a big circle is the open set
Neighborhood.
of infinity. Okay, that's what we're going to copy it here. Nothing more than that. Huh? Okay, before doing that, I can do it successfully for every space. We're doing it for plane. Okay, plane has special feature. I want to bring this special feature into it. Local compactness. A topological space X is said to be compact. Sorry, is said to be locally compact. Local, you understand what I mean by reality? Is said to be locally compact. Okay, if for every X in X there exists a neighborhood G of X whose closure is compact. Neighborhood G of X whose closure is compact. What is that? That is X belongs to G and G bar is compact. I think I can do it in equivalent way. Equivalently, X is locally compact. If for every X in X, there is a compact set that contains a neighborhood of X. There exists a compact set that contains a neighborhood of X. Yeah, this is the compact set. This is the compact set that contains the neighborhood G of X. Yeah, there exists a compact set that contains a an open neighborhood of open neighborhood is open neighborhood for me, right? I'm not. So there exists a neighborhood of X. Okay. Now, suppose I have a locally compact space. Here is one point compactification. Okay. Uh, um, let X be a locally compact space. And I'm going to take an element which is not an X, an object. We'll take an object, an element, whatever you say. Take an object not in X. Let's call it infinity. Let's denote it with infinity. So I have Y is a new space I'm creating, X, and I'm having one extra element, infinity. I'm going to introduce a topology and Y. Okay, I'm going to introduce a topology and Y, which becomes a compact topological space, and X is a sitting inside that. That's what I wanted to do. Okay, this is a little coarse topology. It may not have wonderful properties that the stone state compact equation will have. Anyway, so what is that? We topologize Y as follows. And by we topologize Y by declaring the following sets open. Okay, what sets are open? Open sets which are already open in X, I will allow them all. Okay, all open sets of X. All open sets of X. X has already a topology, right? So all open sets of X. I will say they're open in Y also. Okay. Two sets of the form. I already told you. Sets of the form Y minus C, where C is a compact set in X. Okay. Where C is a compact set in X. Right. Okay. It is X. And I have attached this one point here. Okay. If I want that point to be with me, it should be something like complement of a compact set. You have a compact set here. The whole complement, including with that, is what I declared open set. Okay, in order to say that, of course, in order to say that this is a topology, you have to prove. You have to prove that this is a topology. It's very easy. You take sets of this kind, their unions. Okay, so I just want to prove that such a declaration really gives you a topology. Let's try. Let us claim. I think I can leave all these things for you. Maybe. Let us claim. I don't know. Yeah, almost 12 o'clock. Let us claim the above gives us a topology on Y. It's easy, sir. First of all, finite intersection should be this collection that I have created should be closed under finite intersections and arbitrary unions. Now, let's talk about finite intersections. Suppose I can have sets. If you really go back, both the sets can be open sets in X, and you want to see their intersection is again open. I think that works out. Both the sets can be in this form, and their intersection should be again one of the top form or the bottom form, things like that. Let's come back. I can just do that. So I can have the sets G1 and G2 are open in X. Then G1 intersection G2 is open in X. What is there to do? Nothing to do here. Suppose I have the sets like C1 comma C2 are compacts in X. Then you're looking at Y minus C1 intersection Y minus C2. What is that? It is actually Y minus C1 union C2. If C1 is compact, C2 is compact, their union is compact too. Only finite union. Actually, two things are united. So that's compact. So is open in Y since C1 union C2 is compact. Now I'm going to take a set of this kind, a set of this kind. Uh, G is open in X. C is compact in X. Then I'm going to talk about G intersection Y minus C. Actually, you're talking about Y minus C, right? Sorry, did I? Let's go back. I'm afraid I did something. Locally compact Austin. Excuse me, sir. I need TQ action also to make this work. G is open in X, C is compact. Now you see that these are the elements in G, that means elements in X, and also elements in Y minus C. So what is that Y minus C? If there is anything, that infinity is not there in G. So you might as well write this as G intersection X minus C. But C is a compact set in a house class space, so C is closed. Therefore, X minus C is open. So G intersection, so this is open in X. Whether C is a compact set in a house class space is closed, that means complement is open in X. Both are open in X, the product is there. Intersection is open in X. Yeah. So I think all things are over. Now arbitrary unions. Take G alpha, union alpha, alpha in some delta. If G alpha is open, G alpha is open in X for each alpha in some index in set delta, then union G alpha already is open in X. Open sets in X are okay for me. Now suppose I have C alpha be compact in X for each alpha in some other index in set delta. Then you want to talk about a union union Y minus C alpha, alpha in delta. But remember, this is nothing but Y minus intersection C alpha, alpha in delta. Okay? But this is a compact set, you will see that. Whereas each is a compact set in X. So each is closed. The whole thing is arbitrary intersection of closed sets is closed. Closed subset of any single compact set is compact. This is a compact set. And therefore, okay, right. And notice intersection C alpha, alpha in delta is. So this is one set of this form. Okay. Oh boy, what else is there? I have a collection from there, so maybe I have G alpha open in X. Okay, maybe some other index. This is some index for alpha in delta, and C beta compact in X for some other indexing for beta in delta dash. So I have to look at intersection G alpha, alpha in delta, intersection Y minus C beta, beta in delta dash. What is this? You have to carefully rewrite it, and if you carefully rewrite it, you will be able to understand it. Okay. This is already open, sir. And this is intersection. This is, you just saw that Y minus intersection C alpha. Okay, right? Arbitrary unions. Yes, 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 yes. I want to have arbitrary unions is what I'm talking about, right? Arbitrary, not intersections, arbitrary unions. Okay, okay. So that's it. Then this is also not a bad deal. Sorry, I take it back altogether. So union C alpha, alpha in delta, right? Union y minus C alpha, alpha in, not alpha, beta, beta in delta dash. This is what I want to say is open in the new sense. Of course, this is already open in X union. We just saw that this is a y minus intersection C beta, beta in delta dash. Well, this is a compact set, so y minus this is fine. Okay, I already proved that one single thing. This is open in y. Hmm? This is open in G. So, oh, I see. We're not done with this. We're not done with that. Hmm? With the G union. Hmm? Yeah, yeah, that's good. So this is y minus, okay, G complement intersection C beta, beta in delta dash will do the job. Very good. Because what is this? Y minus G complement is G. By De Morgan law, union Y minus this. By De Morgan, the two are equal. Now you're good. This is a closed set in X, and this is a compact set. So the intersection of a closed set and compact set, this is compact. This whole thing is compact in X. So yes, this is open in the new sense. So this proves it's a topology. Okay. And finally, you have to show that this topology makes Y a compact space. That's also very easy. Okay. So finally, we must notice this topology makes Y compact. That's easy. That's just too easy because if you take any open cover of Y, at least one of the members of that open cover must tend to infinity. If it is infinity, right? So if I take a if okay, uh, if H alpha, I'm always using the same index set. What's the big deal? If H alpha is an open cover of Y, there exists at least one beta in delta, so that H beta is equal to Y minus C beta, where beta is compact, and C beta is compact, and uh, C is compact. This is the one that contains infinity. It's just one of the members you can. So there exists a beta. There exists a beta in delta, such that infinity is in H beta. So how does H beta look like? Okay. Therefore, H beta looks like Y minus C, and C is compact. Hmm? So what happened? Then rest of the H alphas, alpha in delta, alpha not equal to beta, will have to cover okay. See, this is covering what is that? This is covering Y minus C. So this has to cover C, a compact set. Therefore, finitely many of them will cover C. Therefore, there exists alpha 1, alpha 2, etc., alpha n in delta minus beta, such that C is contained in union H alpha k equal to 1 to n. So therefore, the whole Y is therefore is same as union H alpha k equal to 1 to n, union that one extra element I have just had, H beta. So I have finitely many things which is covering Y. Therefore, Y is constant. S plus Y is constant. I hope you got it. Okay, that's it, sir. I think we are able to do that. One point configuration gives you actually, I actually loosely commented that in some sense, well, one point configuration is a very crude and coarse, topology compared to the topology I get and the Stone's configuration. Stone's configuration will be big space into which X is embedded. This is only one point attached in got a compactness. So I think there is a difference in the way they are used. This is very rigid. You have made a, okay. Sir, I'm done for today with all these things. And if you have any, queries or doubts or comments, please tell me that. We will wind up separability here uh, and then come back. I have not given you. Okay, so we'll wind up separability here and move on to connectedness in the next class. Please make your comments or questions.
This one point compactification, essentially, it looks almost like the original topology. We're just adding that few additional things. It's not actually creating a completely new
We said everything
topology.
outside is fine.
Yeah, yeah.
That's what we
Put
said.
everything into one.
So
Whereas,
you cut the whole big topology with this and said these are all okay. Rest of them are all fine. That's what you said.
right, right.
So that's not a really rich topology. Sometimes it works. This is good enough.
So you can use the properties of compact topologies to
Yeah.
solve some problems here,
Yes.
and then map them back to original topology.
Yeah.
Hmm. Okay.
Okay.
Yeah.
We'll get back to you. I have
Yeah.
not given you an example of a regular space which is not completely regular. Actually, I didn't have enough time to think about it well. There are a few examples. All of them are extremely tricky. Huh? So I couldn't fit that in. Maybe if I have a chance, I will do it sometime. There is the
Yeah.
Tikhonov corkscrew is an example in a beautiful book I brought last time by counter examples in topology. He has given you an example of the Tikhonov corkscrew and maybe gave few more versions of that also, which will give you examples for regular topological spaces which are not completely regular. Most of the examples are kind of very uh, quite involved. Okay, so I couldn't give it to you. Maybe in one of the days, maybe if I get to sit and read it well, I'll tell you that.
One thing is I'm coming to Vizag, so Friday we may not be able to have this class,
Yes,
right?
yes, yes, but yeah. We should not have the class on Friday. Huh? Uh, yeah.
Yeah,
Uh, Sai, can you come? Kiran Kumar, I think
yeah.
both Isu
Just
and me are going to be somewhere together too. And we will not have class on Friday. We will meet on Monday again. Okay?
Okay, sir.
That's it.
thank you.
Thank you, sir.
You have a good evening. Bye bye.